just working out the gradient between 2 points on a curve, right? This lesson, we are now going to move into, and this links into the idea of derivatives. So when you learn differentiation derivatives, it follows this concept, except it's called first principles, but the idea is the same. Now, gradients, let's think about it. How many points did I need in order to draw that straight line? What's the minimum number of points? 2, okay? So I need 2 points. Now, when they talk about instantaneous, okay, so not average anymore, instantaneous means exactly in that one spontaneous moment, right? They want you to find the rate of change, meaning they want you to find, well, what if I don't want it between 2 points, but I want to know what is the gradient, say, at P. Can you see that? The gradient that I just drew, this is the gradient at just the 1 point P. Normally, when you're finding gradients, you're finding gradients between 2 points. Now, the question is asking, can we find at this particular point, see, I'm not interested between, say, time of 1 second to 2 seconds. What if I'm just interested exactly at 1 second? What is the rate? Another way of thinking about it is, if you're driving a car after 5 minutes of driving, what's your speed at that moment? So as you're increasing the speed, you're going from 0, stationary, and you're going up to 60 kilometers per hour, which is in your zone. Between 0 to 5 minutes, as you're increasing that speed, where are you at 1 minute? What's your rate at that point is what we call instantaneous rate of change. Okay? So, what is the theory? And I'm just going to give you as an idea, how do we find the gradient at only 1 point when you just said the minimum way to find, or minimum number of points you need to find a gradient is 2, right? And if I only want to find 1, how could we possibly do that? And at the moment, we don't. We can only estimate. Okay, and then you go into chapter 17, they talk about first principles on a theoretical point of view, how it's possible to maybe then find the gradient at 1 point. Okay, so in this exercise, what we see here is that the two gradients are quite different. The orange one is at P, whilst the black line over here, this is the gradient at P to Q. We need 2 points to make a gradient. So how do I get this hypothetical orange line? Well, they're saying, what's interesting is if I move that red dot closer to the original dot, okay, you can see now if I connect all those lines, have a look. So I'm going to connect P to this other red dot. Whoops, there we go, this red dot. And I draw the line. And then I connect it to the next dot. What you should start to see is that I started here. That's my gradient. But as I'm moving the dots closer and closer, and I connect P to that Q, P to the next Q, P to the next Q, what's happening is the gradient is getting closer and closer to the actual gradient I want. True? So theoretically, the number that's most closest, or as we can get, closest to P, so P was 1, and I chose another point that was 1.01, then the gradients must be quite, or at least closer to what we want, correct? Rather than saying 1 and 2, that's the distance, and that's the difference as you go ahead. But if I get it really close, which I make it small, that distance, I'm still using 2 coordinates. But what if those 2 coordinates were so close to each other? Can it be estimated that the gradients are almost exactly just the gradient of 1 point? Okay, now that theory that you're listening to is called first principles. If we then said, let's make it infinitely close. Okay, so that's when I'll introduce in chapter 17, but at the moment, they're not going to get you to make it infinitely close, but what they're going to get you to do is to pick a point that's very close. Okay, so if we have a look at an example, have a look at this. You've got a y equals x cubed plus 1, so I'm just going to quickly draw it so that you have an idea visually what it looks like. So x cubed, remember that's a cubic graph with an inflection point, plus 1, moves up by 1. So this is what my graph would look like. This is my inflection point of 0, 1. Okay. Now from here, I'm just going to make that a bit thinner. So I've got my cubic graph. What they're asking you is P, which is 2, 9, So let's say 2, 9 is over here. So 2, and I'm just going to make it up and say 9 is over here. So that's 2, 9. That's the point P. Notice that the next point that they chose, point Q, okay, point Q is 2.01, and then they wrote 2.01 cubed plus 1. What is this referring to? Does anyone know why they wrote 2.01 cubed plus 1? Where is this coming from?
X equals to
Yeah. All they did was they subbed x equals to this formula, y equals to whatever x is, I cube it and add 1, that tells me the y coordinate. So essentially they're telling you, if this is your first point, 2, 9, what if I chose another point Q that was only 2.01? See how they're making it really close? And by making it close, this is now estimating it may be the same gradient or close to the gradient of P, which is the gradient at 1 point. Okay, so that's the idea. So if I were to answer this question, how do we answer this question? They just want you to find the instantaneous rate of change. And again, we know rate of change. Let's go back to our formula. M was equal to rise over run, or y2 minus y1 over x2 minus x1. Our rules, well, we've got, say this is x1 and this is y1. Then this must be x2 and this must be y2. So on my calculator, I'll be calculating what is 2.01 cubed plus 1 minus y1, which is 9, divided by x2, which I've labeled as 2.01, minus x1, which is 2. See what I'm doing? And all I'm doing is, horizontally, we know the distance between 2 and the next point, which is 2.01, has to only be 0.01 difference. The only thing we don't know is the top. Okay, so now I'm going to use my CAS. So we go. Let's use our CAS and figure out what this potential gradient of at point P would be. So what you're learning right now is called the instantaneous rate of change, because we're estimating for the gradient at only 1 point. Average refers to 2 points. When you're doing the exams or the SACs, how do you know that it's instantaneous or it's the average? If they give you 2 intervals, if they say from t equals 1 to t equals whatever, that means it includes a variety of points. That's an average. Whereas if they only tell you to find the gradient at 1 point, so average rate of change at, and they say x equals 2, that tells you it's instantaneous because you only have 1 point to deal with. Okay, so that's how you normally tell if you're finding the average or you're finding instantaneous. Okay, now let's get out our CAS and I'm just going to put this up. Let's figure this out. We had the fraction. Here we go. Fraction of 2.01 to the power 3 plus 1 minus 9 over 2.01 minus 2. And I'm going to change this to decimals. Yeah. 12.0601. So what does that tell me? What I want you to understand from this exercise here is that this is the gradient. Now I'm going to probably link this a bit to chapter 18 now. So if you're understanding what I'm saying there, what we've just estimated is if I drew what we call a tangent line, so a straight line that touches only 1 point, that tangent line is a straight line equation. Remember straight line equations back in year 9, they followed this. Y equals mx plus c. What you've just discovered, or at least estimated, is m. You've just figured out maybe m is 12.06. Chapter 18, they're going to get you to figure out what the equation of that line is. Okay, so this is where it's going to be special that the more you start to analyze this straight line equation, we start to look at the different types of gradients. Positive gradients, negative gradients, zero, and undefined. That's what calculus is. So in a nutshell, calculus is the study of the gradients or tangent lines for any curved equation. Okay, so in the past, if it's a straight line, it's nice and easy. We already know it's consistent. The gradients, however, on a curve graph, you could have cubics, you could have sine graphs, you could have cos graphs, you could have log and exponentials. you can calculate the gradients on the maximum points based on the straight line equations. That's what calculus is. Okay, so in a nutshell, everything will link back to y equals mx plus c, and if you can understand what I'm trying to describe here, as we're doing differentiation, you're not going to get confused what you're really doing, because at the end of the day, it's only one thing. That's all you're doing. So all the way up to year 12, you're just trying to solve for m. And if you can get your head around that, then the questions aren't that hard. It's not difficult, but time and time again, you'll learn the techniques, but the applying, the understanding of what you're actually doing is what challenges students. Okay, and it's really just to find m. Okay, now out of curiosity, you see, with your logical minds, we've got m right now. So going all the way back to year 9 mathematics, if I wanted you to find the equation of this purple line, we've got gradient. So back in year 9, you were asked to find the equation of a straight line. How would you do it? Because I've given you enough information right now to find the equation of a straight line, and that's chapter 18. You put in?
2 and 9.
And why can you put 2, 9?
Because it's the only point you know for sure is on that graph.
Very good. And that was the only thing that makes chapter 16 different to chapter 18. So it's a very small thing, but if you can be critical about it, this straight line, the only thing we know about this straight line is at 2, that's where it touches. That's the only point that was part of the straight line. When x is 2, y should be 9. So if I wanted to solve this equation, chapter 18, they say, find the tangent equation. All you had to do from this extra step was then to say, well, at x equals 2, y is meant to equal to 9. My equation now becomes 9 is equal to m, which we found out is 2.06, times 2 plus c, and you can work out for c. Differentiation in calculus and all that, chapter 17, chapter 18, chapter 20 that I'm going to teach you, just gets you to find that. Once you know m, the rest is year 9 mathematics. Your job is to get really good at doing that. Okay, and my job is to make sure you're going to get very proficient to find m, and that's chapter 18. Okay, so chapter 16, I'm just kind of easing you into the idea of gradients, but in chapter 17, I'm going to start teaching you different techniques, no matter what graph it is, or more like some of the typical graphs, sine, cos, exponential, logs, anything to do with polynomials. I'll teach you a technique, and your job is to eventually find instantaneous rate of change. That's what it is. Okay, so only using one point, you can find the gradient at any point on any curve, or the curves that we give you, and then you can find out the equation. That's what you're doing. Okay? So I'm going to leave it there. That's essentially the nutshell of what this exercise is. In the next one, for those who do physics, you may enjoy having a look at 16E, where it talks about velocity, difference between position